Hello, dear mathematicians. We are in our series of discussing Fourier series and Fourier transforms. So we are talking about orthogonality of functions. So this discussion will talk about the applications where we talk about the Schrodinger's equation, then talk about the Maxwell's equation that is always seen in electrostatic fields or electric fields. Then we shall look at it also how we use it to solve partial differential equations. Obviously, when we form a partial differential equation like a heat equation, we end up producing a Fourier series. And the Fourier series requires calculation of the Fourier coefficients. And that's where the orthogonality of functions is applicable. Then we shall also look at a few examples, and that will make the highlight of our discussion tonight. Imagine when you're dealing with some quantum mechanics equations like Schrodinger's, the Maxwell's equation, and some PDEs. It's very difficult for you to attack some of these equations head on. You'll find that you have functions. For you, of course, to deal with these equations, you find that you need maybe to compute some coefficients. For example, take a scenario of partial differential equations where you need to solve that partial differential equations, and it leads you to a Fourier series, and which Fourier series has Fourier coefficients. So you'll find that you need to deal with getting the Fourier coefficients. So take an example where you have such a function, and maybe this with respect to x. So you'll find that orthogonality is going to help you in a way that you are not going to attack these functions head on, like direct integration. So if you are doing direct integration, you might spend like the whole day doing this integration. But if you understand some mathematical properties of these functions, then you can just deduce their values. So an example is that if you have two functions being orthogonal with each other, then you'll find that integrating that function over a symmetrical, if you're talking about integrating them over a symmetrical interval, for example, negative L to L of, I'm going to take an example of, I have phi m, then something like this, also of x with respect to x. This is going to equal to 0 for all values of m and n. The other aspect is that if you have two functions that are orthogonal with each other, then those functions themselves have some property also called self-orthogonality. Self-orthogonality, here we are saying, take an example. Integrating over a symmetrical interval again from negative L to L of phi m, okay, of x and phi n of x with respect to x. This is also going to equal to 0 as long as m is not equal to n. That is what we are calling self-orthogonality. In other words, it has got an internal property in itself where the functions, the different states of the same function, you find that they are going to be orthogonal to each other. Likewise, you can have also another function like this. If this function itself is orthogonal, then it is also going to have what we call self-orthogonality in itself. So this is going to be 0, and this is for m not equal to n. So this property holds. These three important properties are going to be used while we are computing Fourier coefficients in the partial differential equations, or when you're dealing with such equations in quantum mechanics, and here this Maxwell's is in electrostatic or electric fields. Electrostatic or electric fields, you'll find that the Maxwell's equation is very paramount. So knowing these three properties, you'll not struggle to find, for example, some particular coefficients if you know that the two functions are orthogonal. How do I tell orthogonality? If I have functions such as f of x is equal to maybe x power 2, that is x squared, and maybe f of 2, x is equal to x cubed. These two functions are orthogonal with each other, because if I integrate, for example, over a symmetrical interval, negative L, let me say negative 1 to 1 of x squared, x cubed dx, I cannot struggle to integrate this because I already know that this is equal to 0. So we are talking about integrating an even function and integrating an odd function. So even function, odd function, they are orthogonal with each other, and this is going to equal to 0. For example, let's maybe do the integration here. This is going to be integrating, this is integrating x to power 5 with respect to x negative 1 to 1. So this is going to be x to power 6 out of 6 from negative 1 to 1. This becomes x, this is 1 out of 6 minus, okay, minus 1 power 6 out of 6. This gives us 0. You can see that obviously gives you 0. So if I'm dealing with an even function and an odd function, and I am dealing with determining coefficients of a Fourier series, then I don't need to struggle if I'm integrating over a symmetrical interval. So where are these properties borrowed from? They are borrowed from orthogonality of a vector quantity. For example, let's look at orthogonality of two vectors. If vector A is orthogonal to vector B, then their dot product is equal to 0. That is a fact. So we can extend this to functions. For example, let's take two functions sine x and sine 2x. If these are going to be orthogonal to each other, then let's represent them on a graph. Let's now represent the sine 2x. So this one will go. So this is 0. Let us say this is pi. This is 2 pi. So this can be half pi. This is 3 pi out of 2. So this is sine 2x and this is sine x. Let's look for the values of these functions over maybe one period. But we can take just a few values. Now, if vector A is represented by, for example, 0, 1, okay, and vector B is represented by, for example, negative 1, 0, then obviously you can see that their dot product is going to be 0. So if you do multiplying these two vectors element-wise, you'll have 0 and you'll have 0. And you'll see that the length of this vector is equal to 0. So similar to when we took the dot product. Now, take an example of these two functions. Maybe you have the values of x ranging from 0, then maybe you have pi out of 40. Make sure that this value is as big as possible. Then you have 2 pi, let me even make it 80 out of 80, 3 pi out of 80, 4 pi out of 80. Let's just take these few and you'll see. So let's look for sine x. Let's look for sine 2x. This is 0 and that is 0. And this is 0.039. And this is 0.7078. And then we go to this. This is 0.078. And this is 0.156. And this is 0.117. And this is 0.233. And this is 0.156. And this is 0.309. So we're going to treat these ones as vectors so that we also look for the dot product. So the dot product here, this is going to be 0, and then 0.039 times 0.078. This is also approximately 0. Then 0.078 times 0.156. This is also very small, 0.0. So this is also approximately 0. Then 0.156 times 0.309. This is also very small, 0.0 something. So you can see that if you sum all of these, you compute all of these up to 2 pi, for example. Or like we started this is maybe over half a period. You can take it up to when you have 80 pi out of 80, so that you have something equivalent to pi. Then you continue, and maybe you can also compute negative pi 0. Then when you sum, obviously what you're going to have is going to be, the sum will be approximately equal to 0. So this is how you can check the orthogonality of these functions. So there I will say that hence, since sine x times sine 2x, okay, this is done over a period of a symmetrical interval negative, maybe, okay, let me say 0 to pi with respect to x. This is going to give us what? This is going to give us 0. So any integral of two orthogonal functions over a symmetrical interval, then that is going to give you 0. And it is very helpful, as I said, that you don't need to go ahead and do the computation. You waste a lot of time. So once you know this property, you just deduce and say this is equal to 0. Then you go to another point that you need to carry out during the process of maybe calculating the Fourier coefficients, in solving partial differential equations, in attacking Maxwell's equation, Schrodinger's equation, and so on and so forth.